So, how do you actually teach a machine to see and navigate all by itself, especially when you take away its most trusted sense? Today, we're diving into the challenge of flying blind and how you can give a drone its very own set of eyes.
I want you to picture this. You have an autonomous drone on a supercritical mission. Maybe it's delivering emergency supplies or it's gathering some vital intelligence. It's relying completely on GPS to know where it is and where it's going. But then, what happens if that signal just vanishes? Does it just stop? Tumble out of the sky?
And check this out. This virtual model of London shows you exactly where that kind of blindness can happen. See, all those tall buildings create what they call urban canyons that can block or totally warp GPS signals. But this isn't just a problem for big cities. You see, the problem with GPS is really twofold. In our day-to-day civilian life, yeah, it's about getting around these dense urban jungles. But in military or contested areas, that signal can be actively jammed by an adversary. And in either one of those situations, the drone is left completely high and dry with no idea where to go. Okay, so that brings up a huge engineering question, right? You can't just send thousands of real, expensive drones flying into buildings to see which ones figure it out. It's way too dangerous, way too expensive. So how in the world do you test for failure safely and actually find a solution for when that drone goes blind? Well, the answer is this absolutely brilliant technique called hardware-in-the-loop simulation. The best way to think about it is like the ultimate flight simulator, but it's not for a pilot. It's for the drone's actual brain, its flight controller. You create this digital twin of the real world, and the hardware flies through this incredibly realistic virtual space, totally convinced that it's the real deal. Okay, so this is what the whole setup looks like. And I know, I might look a little complicated at first, but the core idea is actually pretty simple. You've got the actual flight controller, that little orange box, which is the brains of the entire operation. But it's not connected to real motors or propellers. Instead, it's hooked up to a powerful simulation computer that's pretending to be the drone and the entire world around it. So let's really break this loop down step by step. First, ground control sends a mission to the flight controller, just like it would in a real flight. Then the controller does its job and figures out the commands for the motors. But, and this is the cool part, instead of spinning actual propellers, those commands go straight to the simulation computer. That computer then calculates all the physics, how the drone would move, what it would see, and finally, that virtual sensor data, like what the camera sees, gets sent back to the flight controller. So the controller gets a new camera image, a new position reading, and the whole loop starts over, hundreds of times a second. It's amazing. Now, the real star of the show here, the sense that we're actually testing in this loop, is something called VSLAM. That stands for Visual Simultaneous Localization and Mapping. It's a mouthful, I know, but it's for a simple, incredible idea. Using nothing but a camera, the drone can build a 3D map of its surroundings and, at the same time, figure out exactly where it is inside that map, all in real time. This is the drone's backup eye for when GPS goes dark. And this is where the simulation really proves its worth. I mean, it's one thing to fly on a perfect sunny day, but what happens to the drone's vision when the real world gets messy? How well can its VSLAM algorithm actually see when the weather turns against it? And wow, this image really puts it into perspective, doesn't it? On the left, in good weather, the camera sees all these distinct features, building corners, windows, things the VSLAM algorithm can easily lock onto. But look at the right. In the fog, all those features just disappear. It's like trying to find your way through a fuzzy gray nothingness. So what did the data actually tell us? This chart shows the results. That black line, that's the ground truth. It's the actual path the drone flew in the simulation. And all those colored lines, that's what the VSLAM algorithm thought its path was, using only those camera images we just saw. Let's really break this down. In good weather, that blue line is almost perfectly on top of the black line. The drone knows exactly where it is. But look at the purple line, which is for light rain. The position estimate starts to drift away from reality. And then you get to the fog, the light blue line, and the drone is almost completely lost. It thinks it's flying a nice straight path, but in reality, it's dangerously off course. And this right here is exactly why simulation is such a game changer. Through this test, we found the algorithm's literal breaking point. We learned exactly how much rain or fog it takes for the whole system to fail. And the best part? We did it all safely, sitting at a desk, without ever risking a single real-world crash. Okay, so that's the tech, but let's zoom out to the big picture. Now that we know how to test and build a drone that can navigate without GPS, what's it actually for? What's the real mission here? Well,
a huge application is in a military concept called ISTAR. It stands for Intelligence, Surveillance, Target Acquisition, and Reconnaissance. And what it's really all about is linking up all of your sensors on the ground, in the air, even in space, to give commanders one single, complete picture of everything that's happening. And you see, a drone that can see for itself, that's the perfect ISTAR asset. When an adversary is jamming GPS signals, this autonomous eye in the sky can just keep flying, keep watching, and keep sending back that critical information. It becomes a really resilient part of a very complex network.
But let's be clear, this technology is not just for military use. The implications are much, much broader, and honestly, they're already shaping national strategies all over the world. Just listen to this quote from the Emirates News Agency. It calls autonomous systems a strategic pillar for economic growth. So this isn't just a cool piece of tech we're talking about, it's seen as something absolutely fundamental to building the economy of the future. And that's because we are right in the middle of a global race for autonomy. This is the kind of technology that's key to building truly smart cities, with things like automated deliveries and services. It's essential for creating advanced transportation systems and for making our supply chains way more resilient. At the end of the day, mastering AI and autonomy is seen as a key to future economic power. And all of this leaves us with one final, really critical question. The techniques we've talked about here, the ability to test and to validate these incredibly complex systems in a virtual world, they are the very foundation of this new era. So as these virtual tests become real-world deployments, the question is, who will have the vision and the capability to lead the autonomous future?